All right, welcome back. It's Glenn again, and I'm here to talk to you about some flowing families of curves. Actually, no, today I've got something really cool. Today, for this video, I've got a justification for something that I said earlier, which is what all these videos are about anyway. But this is something very special. What I said before, let's get into it. So I drew these pictures all the way back up here. Yeah, I drew these pictures and I said, well, this can't turn into this because the winding number is different. And our family of evolving curves is very nice and it keeps the winding number constant. So because this has winding number 1, it cannot go to this. And because this has winding number 1/2, it cannot go to this. And vice versa. They can't go back to each other. They exist in a different universe from one another. And I asked you to just trust me. Okay. I also asked you to trust me that there's a formula for this winding number and it's given by this expression. And that is not obvious, but it's true. Anyway, now, assuming that everything that I just said is correct, then if I differentiate this expression with respect to time, you've got to remember, we just calculated the evolution of k. The evolution of k is got 3 terms in it, and they don't look like they are 0. And the evolution of ds is kf plus ts, and that's not 0. So is it true? Is the time derivative of this 0? It should be, because it should be constant with time. Let's find out. That's what we're doing today. And I just think it's beautiful because it's an example of a very deep interaction between analysis, topology, and geometry. I love it. Okay, so let's get to it. Let's see the miracle in action. Here we've got omega. This is the winding number. It's equal to this expression. And let's work out its time derivative. We've got everything that we need, and let's just do it. Let's just work it out. Let's dig in and find it. This is the evolution of the measure. And so we work out the evolution of this integral. This factor at the front is just a constant. It's not going to change the derivative being 0 or not. Either if the derivative is 0, this constant is not going to stop that from being true. And if it's not 0, it's not going to make it true either. So we just ignore the constant. Okay, I substitute in first the expression for the derivative of k that we just worked out. Right, it had these 3 terms in it. Okay, it doesn't look like it's 0. And then I'm going to add on the k times the derivative in time of ds, which is just here. So it should be k times all of this stuff. And you have seen me basically calculate these things from almost nothing. Not completely nothing, but almost nothing. Okay, and this definitely doesn't look like it's 0, right? But let's have a go. First thing we eliminate is FSS. Why? Well, we can use the fundamental theorem of calculus, like we mentioned before, to eliminate one of these s derivatives and evaluate fs on the boundary. Now, fs on the boundary is 0. Why? Because you can differentiate the no-flux condition in time. If you do that, then you're differentiating ks in time, and you're differentiating the angle. If you differentiate the angle in time, that will give you this expression involving the tangent vector, which has an fs in it. It's here, okay? So on the boundary, just imagine what this looks like on the boundary. On the boundary, you've got fs, just by itself, and then k times t. K does not vanish on the boundary in general, but t does. T vanishes on the boundary by assumption. So what that tells you is that because of the angle condition being preserved along the flow, fs is 0 on the boundary. Cool. So this first term is 0. Okay, what about the rest? Well, kf times k is k squared f. It cancels with this k squared f. Cool beans. And then you're left with kst and kts. Well, they're not the same. But look at this little mathematical miracle that has just occurred. I can integrate by parts and move this s derivative from here onto the k. And if I do so, I pick up two extra terms. That's my price to pay. The first price to pay is going to be k times t on the boundary. That will be 0 because t vanishes on the boundary. The second price to pay is that it will have a minus sign. Which is great. It's not a price at all because I'll have minus k as t. It will completely cancel with this term. Look at that. So it's 0. Isn't that beautiful? So there you go. So the time evolution of this is 0. And now let's just sit back for a second. Once you've proved something in mathematics, it's always good to take stock. Now let's think. What are our assumptions? So we've assumed that we have a curve connecting, two parallel lines. It could have loops in it or whatever, but it is 90 degrees. So we have a family of curves like this, and it meets the parallel lines at right angles and has no flux. We did not need to use the no flux condition here. Not at all. But we did use the angle condition. And now what did we assume about our family of curves? Not much in terms of its velocity. If you think about the velocity, it could have arbitrary normal velocity. The f could be anything. We did not use any assumption about the f. And the tangential velocity can be almost anything. It's restricted by the boundary condition, okay? It has to be 0 on the boundary, but otherwise it's completely arbitrary. I find that incredible. So you can mess with this geometric situation quite a lot. You can apply almost any flow to it, and this quantity is unchanged. This, in a sense, this was only discovered. Curvature flow is not very old. It's quite new. But this phenomenon, this topological invariant, is not that old. It's less than 100 years old. And, you could rediscover it like this. You can make your own discoveries. Anyway, that was it. Something fun, something independently interesting, I think. And I hope you enjoyed it. Okay, that's it from me. And also, this marks the end of me catching up on material that was lost because of my corrupted videos. So next time, you're going to see me again writing out live. Okay. Take care, and I'll see you then. Peace.